Welcome to Chapter 5, Section 2, Mean Value Theorem. In the previous section, we defined the derivative of a real function and developed the basic machinery for computing it. In this episode, we prove some of the most useful theorems in all of calculus. The result that the derivative vanishes at interior extrema, the generalized mean value theorem, the mean value theorem itself, and the connection between the sign of the derivative and monotonicity. These results are the basis of nearly every application of differentiation. Let's get started. Here is our plan. We first motivate why we need theorems that connect the derivative to the global behavior of a function. Then we define local maxima and minima, and prove that the derivative vanishes at an interior extremum. With that tool in hand, we prove the generalized mean value theorem and deduce the classical mean value theorem from it. Finally, we harvest the first major payoff. The sign of the derivative controls whether a function is increasing, constant, or decreasing. We close with a summary and a look ahead. Let's set the stage. Everything we did in the previous section was local. The derivative of f at a point x is a limit of difference quotients taken in an arbitrarily small neighborhood of x. So the derivative at one point tells us, by itself, only how the function behaves very close to that point. Here is the natural question. Suppose we know something about the derivative at every point of an interval. Can we draw conclusions about the function on the whole interval? For instance, if the derivative is 0 everywhere, must the function be constant? This sounds obvious, but it needs a proof, and the proof requires a genuinely new idea. The bridge from local to global is the mean value theorem. As you can see on the slide, we will prove 4 results. Theorem 5.8, often called Fermat's theorem, says the derivative vanishes at an interior extremum. Theorem 5.9 is the generalized mean value theorem for a pair of functions. Theorem 5.10 is the classical mean value theorem, and Theorem 5.11 uses it to link the sign of the derivative to monotonicity. Let's begin with local extrema. We start with the key definition. A function f has a local maximum at a point p if there is some positive radius delta such that the value of f at p is at least as large as the value at every point q within distance delta of p. Note 2 things. First, the definition is stated for a real valued function on an arbitrary metric space, not just on an interval. Second, the inequality is not strict, so a constant function has a local maximum at every point. Local minima are defined the same way, with the inequality reversed. The picture shows what the definition means on the real line. The blue curve is the graph of f. The dark red point at the top of the first hill is a local maximum on the green interval on the axis from p minus delta to p plus delta. No value of f exceeds the value at p. The blue point in the valley further right is a local minimum. Note that a local maximum need not be the largest value of the function overall. The curve climbs higher again at the far right. Next, we prove the fundamental fact about derivatives at such points. Here is Theorem 5.8. the basis of many applications of differentiation. It is often called Fermat's theorem. Suppose f is defined on the closed interval from a to b, and suppose it has a local maximum at an interior point x. If the derivative of f exists at that point, then it must be 0. The same conclusion holds at a local minimum. Both hypotheses matter. the point must lie strictly inside the interval, and the derivative must actually exist there. At an endpoint, or at a corner where the derivative fails to exist, the conclusion can fail. One more caution: the converse is false. The derivative of x cubed vanishes at 0, yet 0 is not a local extremum. A zero derivative only marks a candidate. Let's see why the theorem is true. The picture reveals the whole proof. The red point at the top is the local maximum at x. Take a nearby point t to the left of x. The green chord from that point up to the maximum rises from left to right, so its slope is greater than or equal to 0. Now take a point t to the right. The orange chord falls, so its slope is at most 0. As t approaches x, both chord slopes converge to the same number, the derivative at x. A number that is both at least 0 and at most 0 must be 0. The dashed horizontal segment through the peak shows this conclusion, a tangent of slope 0. Let's now write the argument out carefully. Step 1 is pure setup. Since x is a local maximum, definition 5.7 gives us a delta such that f of t is at most f of x for all t within delta of x. Because x lies strictly between a and b, we may shrink delta, so the whole neighborhood stays inside the interval. This is exactly where we use the assumption that x is an interior point. Next, we look at difference quotients from the left. Step 2, take t slightly to the left of x. The numerator, f of t minus f of x, is at most 0 because x is a local maximum. The denominator, t minus x, is negative. A non-positive number divided by a negative number is non-negative, so the difference quotient is at least 0. Since the derivative exists at x, we can let t tend to x, and the inequality survives the limit. The derivative is at least 0. Now we play the same game from the right. Step 3 mirrors Step 2. Take t slightly to the right of x. The numerator is still at most 0, but now the denominator is positive, so the quotient is at most 0. Letting t tend to x from the right gives that the derivative is at most 0. We now have two inequalities pointing in opposite directions, and the conclusion is immediate. Combining steps 2 and 3, the derivative at x is at least 0 and at most 0, hence exactly 0. That completes the proof of theorem 5.8. This little result is the engine behind everything that follows. It lets us convert the existence of an interior extremum into an equation about the derivative. With it, we can now attack the mean value theorems themselves. Here's the first main result, the generalized mean value theorem, also named after Cauchy. It concerns two functions at once. Both f and g are continuous on the closed interval and differentiable on the open interval. The conclusion is that at some interior point, x, the increment of f over the whole interval times the derivative of g at x equals the increment of g times the derivative of f at x. Notice from the first bullet that we need differentiability only at interior points. Continuity at the endpoints suffices. This weaker hypothesis costs nothing in the proof and is often useful. Before the proof, let's plan our strategy. Let's understand the plan before diving in. The desired equation says that a certain combination of derivatives vanishes at x. So we build one auxiliary function, h, whose derivative is exactly that combination. The function is designed so that its values at the two endpoints agree. The increments of f and g cancel each other. Then we bring in theorem 4.16 from chapter 4, shown in the gray box. A continuous function on a compact set, such as a closed bounded interval, attains a maximum and a minimum. If h is not constant, at least one of these extrema must occur strictly inside the interval, and theorem 5.8 forces the derivative of h to vanish there. Now the details. Step 1 defines the auxiliary function h. It is a fixed linear combination of g and f. The increment of ef over the interval multiplies g of t, and the increment of g multiplies ef of t with a minus sign in between. The coefficients are constants, so h inherits continuity on the closed interval and differentiability on the open interval from f and g. Note that the derivative of h at a point is exactly the expression we want to prove equal to 0. Next, we check the endpoint values. Step 2 is a small computation. Evaluate h at the left endpoint. The cross terms f of b times g of a and f of a times g of b survive, while the products of values at the same endpoint cancel. Evaluating at b gives exactly the same expression, which is equation 12 on the slide. So h takes equal values at the two endpoints, just as the strategy demanded. Incidentally, a differentiable function with equal endpoint values is exactly the setting of Rolle's theorem. Our auxiliary function was engineered to land in that special case. The theorem is now reduced to a single claim. The derivative of h vanishes somewhere strictly between a and b. We prove this by considering 3 cases. Step 3 splits into cases. If h is constant, its derivative vanishes everywhere, and we are done. Otherwise, suppose h climbs above its endpoint value somewhere inside the interval. By theorem 4.16, h attains its maximum at some point x of the closed interval. The maximum value exceeds the common endpoint value. So by equation 12, the point x cannot be an endpoint. It must be interior. And now, theorem 5.8 does its job. At an interior maximum, where the derivative exists, the derivative is 0. One case remains. In the last case, h dips below its endpoint value somewhere inside. Then we pick x, where h attains its minimum. Again, equation 12 forces x to be interior, and theorem 5.8 gives a vanishing derivative. In every case, we found an interior point where the derivative of h is 0. Unpacking the definition of h, that equation is precisely the conclusion of the theorem, boxed at the bottom of the slide. Notice how little we assumed. No differentiability at the endpoints, and no assumption that g prime is non-zero. Next, the most famous special case. Here it is. The mean value theorem, the special case that gives the whole section its name. If f is continuous on the closed interval and differentiable inside, then at some interior point, x, the increment of f over the interval, equals the length of the interval times the derivative at x. Dividing by b minus a, the statement says the average rate of change over the interval is achieved as an instantaneous rate of change somewhere inside. Think of driving. If your average speed over a trip was 60 miles per hour, then at some instant your speedometer read exactly 60. In geometric language, written below the box, some tangent line to the graph is parallel to the second line joining the two endpoints. A picture makes this vivid. Let's read the picture. The blue curve is the graph of f on the interval from a to b. The gray line is the secant through the two endpoint values marked by blue dots. Its slope is the increment of f divided by b minus a, the average rate of change. The orange line is tangent to the curve at the interior point x, marked in red. and it is parallel to the gray secant. Its slope, the derivative at x, equals the second slope. The theorem promises that such a point x always exists, though it does not tell us where it is or whether it is unique. The proof is now a one-liner. The proof is delightfully short. In the generalized mean value theorem, choose g to be the identity function. Its increment over the interval is b minus a, and its derivative is 1 everywhere. Substituting these into the conclusion of Theorem 5.9 gives exactly the mean value theorem. This is a pattern worth remembering. Highlighted at the bottom of the slide, sometimes the cleanest path to a classical result is through a more general statement whose symmetry makes the proof easier. Now let's collect the first major payoff of the mean value theorem. Here is the payoff. Suppose f is differentiable on an open interval. Part A says that if the derivative is non-negative at every point, then the function is monotonically increasing. Recall from Chapter 4 that monotonically increasing means whenever one point is less than another, the value of f at the first is less than or equal to the value at the second. This is the rigorous version of the intuition that a non-negative slope means the graph never goes down. Two more parts follow the same theme. Part B answers the question we raised in the motivation. If the derivative vanishes at every point of the interval, the function is constant. This sounds obvious, but note that it is a genuinely global statement, and without the mean value theorem, there is no direct way to pass from the local information. All difference quotients tend to 0. To the global conclusion, the function never changes value at all. One more part completes the picture. Part C is the mirror image of Part A. A non-positive derivative everywhere means the function is monotonically decreasing. Together, the three parts say that the sign of the derivative, checked point by point, controls the global shape of the function on the interval. This theorem is the foundation of curve sketching, of optimization, and of countless uniqueness arguments later in analysis. Let's look at a picture and then see how all three parts fall out of a single equation. In this picture, the blue curve has non-negative slope at every point. The orange segments are tangent lines, and every one of them tilts upward or is flat. The claim of Part A is that the curve as a whole can then never descend. Pick any two marked points, x sub 1 and x sub 2, with x sub 1 to the left. And as the dashed levels on the vertical axis show, the value of f at x sub 2 is at least the value at x sub 1. The mean value theorem is exactly the device that converts the pointwise slope condition into this two-point comparison. Here's the proof. The whole proof is one application of the mean value theorem. Take any 2 points, x sub 1 less than x sub 2, inside the interval. On the closed interval between them, f is differentiable, hence continuous. So Theorem 5.10 applies. The difference of the function values equals the positive factor, x sub 2 minus x sub 1, times the derivative at some intermediate point, x. Every conclusion can now be read off from this single equation. Now read off the three parts. The factor x sub 2 minus x sub 1 is positive, so the difference of function values has the same sign as the derivative at the intermediate point. If the derivative is non-negative everywhere, the difference is non-negative. So f is increasing, that is Part A. If the derivative vanishes everywhere, the difference is 0 for every pair of points, so f is constant, Part B. If the derivative is non-positive, f is decreasing, part C. Since x sub 1 and x sub 2 were arbitrary, the proof is complete. Let's review what we covered. First, Theorem 5.8, Fermat's theorem. If a function defined on an interval has a local maximum or minimum at an interior point, and the derivative exists there, the derivative must be zero. The proof compared the signs of the one-sided difference quotients. This is the tool that locates candidates for extrema and powers the proofs that followed. Second, the generalized mean value theorem. For two functions continuous on the closed interval and differentiable inside, the increments and derivatives balance at some interior point. The proof technique deserves its own mention. Build an auxiliary function with equal endpoint values, then apply the extreme value theorem and Fermat's theorem. Auxiliary functions of this kind reappear throughout analysis. Third, the mean value theorem itself, obtained from the generalized version by taking G to be the identity. Somewhere inside the interval, the instantaneous rate of change equals the average rate of change. Geometrically, some tangent is parallel to the second. This is the bridge between local information about the derivative and global information about the function, and it is arguably the most frequently used theorem of differential calculus. Finally, Theorem 5.11. The sign of the derivative controls monotonicity. Non-negative derivative means increasing. Identically zero means constant. Non-positive means decreasing. And all three conclusions fell out of one application of the mean value theorem. In the next episode, we ask a subtle question. How badly can a derivative be discontinuous? We will prove a surprising result. Every derivative, continuous or not, satisfies the intermediate value property, just like continuous functions do. See you there.